workshop started, everyone. So, Jerry has a couple announcements.
Cool. Hello, everyone. Welcome to the first workshop of Screen Quarter. These are a couple of things that they'll be talking about this workshop. As you guys see, screen is in the air. Before we get started with the workshop, I wanted to go around and have everyone meet the new leadership. So if you're an officer, can you stand up, and then we'll just go around and say our names. So I'll start. My name is Jerry. I'm one of the co-presidents. The other co-president, Stephen, unfortunately cannot make it today. But yeah, we can go around.
All right. Yeah, I'm Nick.
I'm Salma. I'm Juliet.
I'm Benson. I'm Rory.
I think that's everyone. Hello, come on in. And then one last announcement is, if you guys didn't know, we have a competitive CTF team called Psi Beta Rho. And the signups for that are due by this Friday. If you're interested, you can check out the slides that Benson posted in announcements a bit ago. It's gonna be really cool. All you basically have to do for the entire quarter is attend one CTF and then do some extra small miscellaneous tasks. But yeah, it'll be really fun. All right, you guys can take it away with your workshop.
All right.
Cool.
Yeah, go for it.
Oh,
Yeah.
Cool. So before we begin, we just wanted to make a little bit of clarification. For this workshop and for CS33, we're going to focus on x86-64 for the ISA. There's two main computer architectures. You have the CISC and the RISC, and basically the complex one, there's fewer lines of assembly, but you're going to have more cycles per instruction. So that's good for really complex operations. Whereas RISC, it's good for quick, simple computations. So each instruction is going to take less time to run, but you're going to need more lines of assembly. So your code might look more convoluted. And so the x86-64 that we're focusing on falls under CISC. And the big idea of today's workshop is that we're moving from hardware to software. We want that middle part. So as things become more towards the software side, there are going to be higher levels of abstraction. So for abstraction, you might think of it as being more human readable or easier for humans to use. So whereas something like ones and zeros, that's kind of hard for humans to just straight up interpret. That might be closer to the hardware side. Whereas if you've ever used drag and drop software like Scratch in middle school, high school, or anytime, that's very abstract. That's very on the higher side. And today we're going to be looking at how to translate between hardware and software and into binary.
All right, so before we get into assembly, we're going to talk about the compilation pipeline a bit. So basically what happens in the compilation pipeline is we go from human legible C code or Python code or whatever you're writing in to machine interpretable binary. So each step's output will be the input for the next step. You've got 4 steps: the preprocessor, compiler, assembler, and linker. So I'm going to go through all of those and then show you what each step looks like at the very end in more detail. So let's see, how do I go to the next slide? There we are. So the first phase is the preprocessing phase. So what happens during the preprocessing phase? The code at the end is going to look quite similar to your original C code. What it does is it just modifies the original program according to directives that begin with the pound symbol, like include studio.h. Or things like that, anything that you choose to include. So these lines will then be interpreted as preprocessor commands and form a simple macro language. So what the macro language does is it provides a very convenient way to generate a sequence of an assembler language statements many times in one or more programs, which will simplify the coding and reduce the chances of programming errors. So let's see. It also copies the header files into the source file and deletes comments, produces another C program with a .i suffix, which I will show you at the end. This right here is just our regular C program because the other one is a bit longer, so it wouldn't fit on the slides. So our next phase is the compilation phase. So what our compiler does is it translates the .i file into a .s file containing the assembly language program, which is what we're going to be looking at a lot in CS33 and throughout the rest of this workshop. We're going to go into more detail about the structure and meaning of each line of the assembly later, but the assembly will be specific to target processor architecture, so like CISC versus RISC. And it is still legible by humans, so it is not yet machine readable. So this is sometimes known as the immediate representation code. And generally, assembly will serve as a common output language for different compilers and different high-level languages. So you will get very similar looking assembly code for, say, a program that was written in Python versus a program that was written in C that was designed to do the same thing with the same sorts of steps. So after that, we're going to run into the assembly phase, which this, by the way, right here is our .s code. So what the assembler does is it translates our assembly into machine language instructions. So these machine language instructions, they're not very pretty, which is why they're not on here, but they're packaged into a relocatable object program and stored in an object file, aka .o. So these instructions are interpretable by the machine, written in binary format, but the overall program is still incomplete. Why is that? Well, because we haven't linked everything together. So that takes us into step 4, the linking phase. So this phase will produce the final executable by it will take one or more object files or libraries as input and combine them to produce a single executable file. So in doing so, it will resolve references to external symbols, assign final addresses to procedures and functions and variables, and revise the code and data to reflect a new address with a relocation. So this can be done through static or dynamic linking. So these both have their different pros and cons. What static linking does is it makes a copy of all the used library functions directly into the executable file. And what the dynamic linking does is it does not directly copy the code. It just sort of places a pointer to the library in the executable. And the dynamically linked files are brought in at runtime. So static will use more space and it sometimes will take longer, whereas dynamic linking can have compatibility issues. I believe most things do use dynamic linking, but either is usually fine. So the final product will be ready to be loaded into memory and executed by the system. How do I pull up the? Okay,
Let's
pull up
see.
this stuff.
We're going to show a little example of what she's talking about. I think if I do that, that'll work. No, it is.
Oh, there it is.
There we
Oh,
go.
Interesting. Okay, so basically up in the upper left corner, we've got our C code for hello world. And over there, we've got, this is why I didn't show it on the slides, our .i file, which is quite a bit longer because it takes this, includes studio.h, and basically it gets it all in there. So we have a whole bunch of code, including all of that. And then once we get down to the very bottom, it will, okay, we there yet. Okay, there's a lot of stuff. How do I scroll with two fingers?
Just like,
Oh, I don't know how to use Macs.
okay, fair enough.
This was an Emacs. I could go. Okay. TLDR, it's going to have that at the bottom. I'm not scrolling all the way down. But in the bottom left-hand corner, we've got our assembly codes. This might look familiar to you a little bit from CS33, but this is all sort of human readable. That is, no, it's not perfectly human readable, but sort of is. And here we have our object code, which as you can see is a total mess. But this will be interpretable by the machine. It's not complete, and I do not have the full executable on here because it would look kind of similar to that, also very unreadable. So compilation pipeline.
Cool. All right. We are almost to the point where we can talk about assembly code, but I have a couple other things to talk about first. So let's get into CPU architecture. So any modern day computer uses a von Neumann architecture, which is general purpose. What this means is you can input some code and it'll run that code and output something. You can input some different code and it'll run that code and output something else. This seems pretty standard today, but an example of something that's not general purpose would be like a desk calculator. If you want to go change the function of the plus key, you'd have to go physically change around some circuits, which is slow and inefficient, not what you want to do. So this was actually a pretty big innovation many decades ago, and it's what we still use today. Some important components of the von Neumann architecture are the control unit of the, or sorry, we've got a computer with input and output. So that could be a keyboard and mouse, or it could be like reading from a terminal. And then output could be a screen or a terminal again. And then we have inside the computer a CPU, which has a control unit, which is in charge of executing cycles in the CPU. So the way a program runs is it fetches one cycle and then it executes that, or it fetches one instruction and then it executes that instruction and then it fetches the next instruction in this continuous loop. So we have this control unit in charge of fetching those cycles and running them. And then we have the arithmetic unit, the ALU, arithmetic logic unit, that is. This unit is in charge of arithmetic. It does addition, subtraction, etc. And these are all within the CPU. Do I have anything else important here? Don't think so. All right. So on a CPU, there are registers. And registers are like very high speed locations on a CPU. They're even faster than memory. These are kind of the necessary components to doing any operation on a CPU. So as you can see here, there are 16 registers on a modern day, or these are the 16 general purpose registers on a modern day 64-bit CPU. A register is 64 bits on a 64-bit CPU. And as we can see, each register here is a row. And then I also have it split up into columns based on these different partitions of the register that you can access. Let's see if I can hide that menu bar. Let's see. So we can see, yeah, we have RAX, for example, that first register up there is 64 bits. And then if we want to access the lower 32 bits of it, we type in EAX. If we want to access the lowest 16, it's AX, and then AL. And then there's this AH, which is only for the first 4. There for compatibility reasons, and that lets you access the top half of those 16 bits. It's important to note that EAX is within RAX. So if you modify EAX, it'll also modify the lower 32 bits of RAX, and it will do nothing to the top of RAX, which is an interesting little note. So yeah, these are important. You'll kind of see why we use them in a bit. Essentially, you have to do your operations, your arithmetic with these registers because they're on the CPU and they're like what the arithmetic logic unit, for example, can interface with. And of course, the CPU can also access memory and manages the cache. So memory is on the system. It's where your program has its code running and where it has relevant data that you're working with. And the cache is kind of in between registers and the memory. It's an area where the memory is cached and it's quicker accessible by the CPU. You know what I'm saying? All right. And a couple other registers that are important on a CPU that we won't get too much into detail today, but they're good to know about. There's the instruction pointer register, which is used on that, as I was talking about, oh, my mouse is over there. As I was talking about before, we have the control unit. There's an instruction pointer register, which points to the specific instruction that's currently being executed. There's the flag register, which is used for, as you'll see later on, like addition with carrying. You'll see what I mean in a second by that. And there's XMM registers, which are used for floating point operations, which is a whole nother story. When you have a decimal, it's really screwy with computers. All right, so we're almost getting into the actual assembly code. In assembly, variables are only numbers. You might be used to having strings or classes in higher level programming languages. In assembly, all we have is numbers. You're probably used to bytes. You're probably used to those words, but we also have words, double words, quad words, and double quad words in assembly. These are simply just various sizes of data. A register, for example, stores a quad word worth of data. And you can access those lower portions to store a double word or a word or a byte. If you want to store a string of text, that would be a consecutive list of ASCII characters, similar to a C string, if you're familiar with those. So every character has a number associated with it, and it's just a consecutive bunch of numbers in memory for your string. And yeah, any questions about that so far? All right, so there are two types of variables. The first one is those initialized at compile time, and these are in the data section of the program. This is at the very top of your program. You write section.data, and this is where you can declare your variables. So, so we want to make a word, a variable that is a word in length and size. We use my word right here to say the variable name, and then the size of it is DW. So this is saying it's a word. We're kind of declaring a word. I'm not quite sure what the D comes from, but we've got different sizes of variables here. And then 5,000 is the value we're putting in it. If we want to have 3 consecutive places in memory, we could do commas between different values. These are all 3 different bytes. If we want to do a string, assembly does actually support you putting a string in quotes, but this will just get the ASCII values of the individual characters and then place them simultaneously in memory or consecutively in memory. And if you want constants, you don't actually have to specify the size. It'll figure that out for you. Use the word EQU. You can't modify that later. All right, the next section is the BSS section, which is uninitialized variables. So in C and most higher level programming languages, you're probably used to writing like int x and int x equals 5 on like, I don't know, lines right next to each other. That's fine usually. In this case, in assembly, you have to keep those separate, the ones that have a value initially when you make them, and those that you're going to initialize later. So the BSS section is the next section of your program. You write section.bss to go to that section. And this is where you can initial or reserve memory for specific variables. So as you'll see, on our previous slide, we had db, dw, dd, dq, and ddq for the different sizes of variables. But I don't know, maybe as Carrie Natchenberg would say, maybe someone was smoking something when they made assembly. We've got up here resb, resw, resd for the sizes in the BSS section. Not sure why, but essentially it's a similar format. You've got your variable name and then the size of the variable. So this will create a variable called myArray and it'll reserve byte sizes of memory and it'll reserve 10 of those bytes. So we've got, yeah, myArray and it has 10 bytes memory. Down here we have the equivalent in C. We're making an array with 10 bytes. We're doing char because that's what the byte size is in C. And yeah, one other important thing to note about variables in assembly code is that the actual name of a variable in assembly refers specifically to the address of the variable. So to access the value of the variable, you're going to have to do this sort of syntax here. So you'll say the size of the variable. And once again, this is different from the size here. So you actually spell out that size. So byte of myArray will get the value of myArray, and then it'll get a byte of it. And this is, for example, a double word of the variable dvar. What's up, Benson?
So just to clarify some accuracy, so unlike C and C++, where you declare a variable of the type, specific like data type as a string, you have to like keep track of the amount of bytes you can assembly to define it. Initialize it out of memory for a particular to initialize it to.
Yeah, I mean, yeah, you kind of have to, so to clarify or to restate, Benson was asking just, do you have to kind of keep track of what size of variables you're initializing? And the answer is yes. You can't really, I mean, all you can work with is numbers in assembly. So you just have to know what size of whatever data type you're trying to work with is and create a variable of that size or create an array of 10 elements if that's how much space you need for that data. And a lot of what you're doing with assembly is just manipulating numbers. Higher level languages make it really easy to convert just this really low level number manipulation into actually like human readable like classes and stuff, which is really cool. Because initially we were just doing this. All we could do is like, basic math, and we've coded on top of it words and pictures and videos and stuff. So there's been a lot of abstraction going on that's made computers a lot more powerful. But yeah, at the lowest level, it's just numbers. What's up?
So when it says uninitialized variable, does that mean that it's still like a fixed size variable, so it's not that it get activated?
Yes. So yeah, you can't change the size of variables after you've declared them. This is just saying that they don't have a value yet. All right. Next section, we can finally get to the code of assembly. So you type section.text, which is the text section, and this is where the code is. In Linux, you're going to need to write those 2 lines of code to kind of get the entry point for your program. So in C or C++, you have your, either you have your int main function. This is your entry point in C++. When you run a program, it knows to start there. In assembly, you have to write those 2 lines, and it'll start right after that _ start. And _ start is a label, is what that's called. So this is a place in the program that you're kind of just writing down and noting for later. So yeah, it's under the hood, it's actually an address, but if you ever reference _ start later in code, you're actually pointing to just that location and nothing more. We'll use those a little more very soon. All right, I'll pass it off to Juliet.
All right, so something that's been emphasized a lot in class, if you have attended lecture, is the difference between MOV and LEA. Not sure how to pronounce them, so I'm going to go with move and Leah. But basically, move copies data at an address, the first one, your source address to the destination, whereas Leah kind of copies the address itself. So I like to think of it, this is kind of an imperfect C analogy. It's not super accurate because if you get into like the details, there's stuff about pointers and registers and stuff, but it doesn't carry over perfectly. But you can think of it as move, you're copying what's actually inside of the address. So that's why you have like a little asterisk. If you remember in C, you do that to get inside of an address, kind of like what the value is. Whereas for Leah, you're kind of just getting the address itself. And unlike Leah, move dereferences. So if you have those parentheses, you're going to look at what value is stored inside of the register. Whereas for Leah, you don't actually go inside. You're kind of just using the address itself. I'm not going to go into too much detail with this table, but you can look at the slides. And I think it gives a pretty good comparison of the two. So like, for example, if you were going to look at the second row, it has the source operand with 2 registers and then a destination operand. So the first one, if it said like move and then it had all that stuff, you would be going to the address. So you would look at what's in RAX, add that to what's in RCX, and that will give you like some random number. You're going to go to that number, look inside of that address. And that is the stuff that's inside of the summation, I guess, is what you're going to put into the register RDX. By contrast, LEA, you're going to copy what's in like kind of both of them combined, like the address themselves into RDX. And if you have any questions, we can go over this a little bit more in detail later. But something that we wanted, oh, yes, Benson.
Oh, it's okay.
Okay, cool. Just something that we learned 30 minutes ago before this workshop, really fun timing, is that there are 2 different syntaxes. There's Intel syntax and AT&T syntax. So Intel syntax, so one example of a difference between the 2 is that when you have your move, you put the destination before the source, but for AT&T, you put the source before the destination. This can be really confusing. We have 2 examples of what that might look like below, but in CS33 and Linux in general, we use AT&T syntax. So if you do see some differences, just know that they're saying the same thing, it's just different syntaxes. If you see like % signs and $signs, it's probably an indication of AT&T. Like they can be used in Intel, but it's optional. And that might just be a source of confusion. So, all right. And on this slide, there's a really simplified example. We're missing some of the headers that you saw earlier, like section.txt and stuff. But this is good for reference. If you need to look back at the slides, these are pretty cool. I'm not going to go too much in detail because we have some demos at the end that will help you visualize this. Okay, cool. Now it's time for addition and subtraction. Yay. Okay, so before getting into that, we need to make a distinction between unsigned and signed integers. So we have this nice wheel over here. It's only representing 16 numbers, I believe. That's 4 bits. I would not have had room to fit 32 bits onto the screen, or just be really tiny. But the outer ring is your unsigned numbers. These are your normal binary to decimal conversions. So you know how like normally when you're counting, you have your ones, tens, hundreds place, whatever. For this one, you have your 2 to the 0, 2 to the first, 2 to the second, etc. For this one, you'll notice that the highest bit, the 2 to the third, is a positive number. And so because of this, you can have, if you have like binary 0, 0, 0, 0, it's going to be 0 in decimal. And then if you have binary 1, 1, 1, 1, it's going to be 15 in decimal. And then by contrast, you have your signed integers, which are represented in 2's complement form. And that's represented by the middle ring here. And the biggest difference is that the first bit, or the most significant bit, instead of being positive, is negative. So you're gonna have a really, really big negative displacement if there is a 1 in that place. And I like to think of it as like it displaces it a lot in the negative direction if you have a 1, and then the positive bits are trying to get it back to 0, kind of. So that lets you represent -8 to 7, and you'll notice that that is an asymmetrical range, meaning that you can represent more negative numbers than positive numbers by 1. Okay, cool. So addition, we have carry and overflow. So carrying is pretty simple. It's pretty similar to what you would do in decimal, except you're only working with 1s and 0s. So instead of like, 9 plus 1, you do like 0 and 1. You're doing just, if you get 1 plus 1, you have to carry. So you can kind of see how that works. If you look at the green row, it's 0, 1, you get 1, 1, 1, you get 0, and there's an overflow, so you carry it over. And then with this overflow, a helpful way to think of it is kind of like a clock. On a clock, you only can represent 12 numbers. So once you get to that point, you have to kind of restart over. That's a helpful way to think of overflow. So for example, if you were adding 15 to 15, if on the wheel over here, if you start here at 15 and you went around by 15 spots, you would actually end up on the 14. And then if you look at the result, it is 1110. So to think of it as kind of overflowing and going back to negatives or positives is helpful. And then subtraction is pretty similar. It's like fancy addition. You just negate the second operand and add that to the first operand. If you're in 2's complement form, that basically just means taking the complement and then adding 1. So taking the complement, you know, like reversing all the bits. So if it's a 0, you're going to replace it with a 1. 1, you're going to replace it with a 0, etc. And that's just an example right there. Okay, cool. And then here are some commands. If you were looking at the assembly language, you might see add, destination, source, increment, subtract, and decrement. So increment and decrement would just be like, you know, if you have an index counter and you're doing I++ or I-, stuff like that. This kind of shows you how the programming language would be translated to the assembly language. Notice the section headers, as well as how you might be moving stuff from one place into another and using the registers. And again, this is the syntax that we're not actually covering in class. This is Intel syntax, but the idea is the same. For the one we're covering in class, you'd probably see like add source, comma, destination instead.
Okay, so now we've got multiplication and division in assembly. So we're starting off with multiplication. Multiplication does treat signed and unsigned multiplication differently. So we've got mul for unsigned and imul for signed. So basically what happens in multiplication is this is where registers like are kind of important. Your multiplicand will be placed in the RAX register and it will be multiplied by some source value in another register. This other register can be arbitrary. It doesn't really matter what it is. And your result after the multiplication will end up in the RAX register again. So in signed multiplication, IMO, all your operands will be treated as signed. And I've got some syntax here. Again, this is in Intel syntax. But the idea would just be the same. It would just be flipped in AT&T syntax. So we've got mul source, which just multiplies whatever's in RAX by the source. Imul source, which is just signed multiplication. Then you have imul destination source or source destination in AT&T. And then this one over here, which is imul destination source immediate. So first of all, let me explain what an immediate is really quickly. An immediate is just like a regular number. In AT&T syntax, it'll usually have a $ in front of it to represent the fact that it's an immediate, but in Intel syntax, we do not have that. So basically what this does is it'll multiply your source by an immediate and place it in destination. So here I've got a little example of multiplication in assembly. So over here, we declare our variable x is equal to 5. It's an unsigned integer, so we're using unsigned multiplication. We put that into RAX, and then we'll put 5 into our dx, which is our arbitrary register. Once we do mul rdx, it'll replace what's in RAX with 25, and then we'll move that value back into x. So x will now be 25 after this. So next up, we've got division. Division sort of works like multiplication, except it's a little bit different. So I've got to make sure to explain this lower bit really well. So again, there are 2 instructions for dividing data, which is sort of like how multiplication handles it. We've got division unsigned, then I division for signed. In order to do division, your dividend must be larger than the divisor, otherwise you'll have problems. And then in case of overflow, the processor will generate an interrupt, so it is not great to work with if you use division. So what this process does that's a bit different than multiplication is it will generate 2 values. It'll generate a quotient and a remainder. So this is useful if you're running, say, the modulo operation, you're looking for your remainder. That's why you need division. So basically the storage location of these values and the dividend will depend on the size of the divisor. So if you have a 1-byte divisor, your dividend will be placed in AX, and your quotient and remainder will be placed in AL and AH respectively. So quotient in the lower 8 bits, remainder in the higher 8. One word, your dividend will be split between registers, so it'll be half in DX, half in AX. So your quotient and remainder will be placed quotient in AX and remainder in DX. And the double word, your dividend will be split between EDX and EAX, and your quotient and remainder will be EAX and EDX. Your compiler will know where all this stuff goes. It deals with it for you. So it'll make sure everything's placed in the right spot. So over here, we've got some syntax for division. Division source, which divides. This says RAX, but it's really whatever we have going on wait, never mind, my bad. But yeah, it divides RAX by the source, and if it, IDiv divides dividend by the source, but it's signed division. So over here, I've got to make sure I explain this well, but basically your X is a byte here. So you're supposed to put it in AX, but because it's a byte, it's only 8 bits and AX is 16 bits. You have to make sure to zero out the entirety of AX before you move it in. So that's what this goes on here. So you've got your AX register, and then right here, it's your AL register. So first you zero out the AX, and then you put X into the AL register, which is basically the same as putting into the AX register, but since it's only 8 bits, you just stick it in AL, if you catch my drift. So basically, you zero that out, you move X into AL because that's where it's supposed to be according to this step over here. That's the same as AX, don't worry about it. Then you move 2 into some arbitrary register. In this case, I put it in BL, and then div BL will put 3 into AL, and I believe it will put it'll put 0 into AH. So after that, we move the quotient back into the variable, and we're done with division. Also, if you have any questions, please ask.
Yes, any questions about all of that? Division, multiplication, addition, subtraction. All right, just a few more things, a few more instructions in assembly before we get into the demos. So I'm going to talk about control statements, which is they control the flow of a program. So we have unconditional control. It's pretty basic. If you have a label like start loop up there, and you want to jump to that label, you want to go somewhere else in your code, you use the jump statement, JMP, and it just goes directly to that code. So this right here is an infinite loop. You don't even need the inc RAX. It'll loop forever with just this and this right after each other. So that's why this just goes down forever. There's that. More useful, more interesting maybe, I mean, jump is useful, is conditional control. So if we want an if-else statement in assembly, it's not as easy as writing if condition, do this, else, do this. We actually have to use 2 different statements, maybe even more if we want that else feature or that else functionality. So first off, we have to compare 2 operands. So this we can compare, say, in this example down here, we have A and B. We can compare A to B. And then based on the results of this comparison, we'll either choose to jump or choose not to jump. So I'm just going to run through this code. It's easiest with an example. We have A starting at 0 and B starting at 5. We put A into a register because this compare instruction requires that at least one of the values be in a register. And then we just compare RAX, which has the value of A, so it has 0 in it, to B. So we're comparing 0 to 5, A to B, 0 to 5. And then we're doing JLE right here, which means jump if less than or equal to. So if A is less than or equal to B, we're going to jump to that less statement. So in this case, A is 0, B is 5. It's going to indeed run the jump if less than or equal to, and it'll skip over this line here and just go straight down to less. Say A had been 10 instead of 0, then A is no longer less than or equal to B. So it would in fact run this MOV statement, and looks like that'll put whatever's in B into A, so it would set A to 5, and they'd both be equal to 5. Doesn't really matter about that. What's important here is that if the condition is true, it'll jump over whatever code to wherever that label is. Otherwise, it'll just continue running down the program. And yeah, what's up?
I have a question. So if it went into the else case, and if it did that line under like the move,
yeah,
it looks like it would also just the less, and it would run the less colons.
Yes,
so you have to like jump over the less.
Yes, you're totally correct there. So yeah, in this case, it's kind of like if this, then it'll do the less code, and else it'll do this code and the less code. If you wanted it to be like a true if else, you would have probably another label down at the end past your less code, and have a jump statement right underneath this move before the less, and jump past that code down there. If that makes sense. Cool. And then these are all the jump statements. There's a good amount of them. Jump if equal, jump if not equal are pretty self-explanatory. And then we have versions of jump for signed and unsigned comparisons. So if it's signed, we have jump less and jump less than or equal to, and jump greater and jump greater than or equal to, which is self-explanatory. And then if it's unsigned, little easy way to remember it is jump below and jump above. Yep, that's that. Look at all those businessmen in their suits. All right. So that's most of it. That's pretty much all that we're going to cover today for assembly code instructions. Couple other ones we have and, or, XOR, not, which are just their bitwise operations. And then this might be less useful now that we figured out that all of my notes from taking this class in the past are with Intel syntax, and now you're going to have AT&T syntax. But if you want a bunch of notes, they're here. This will give you some reference on what you're doing today, and maybe helpful in the class later on. All right, so I'm going to pass it off to Salma for our first demo.
Okay, I don't want y'all to leave me hanging here. This is going to be interactive, so I'm going to ask y'all things. So we've got some, it's incomplete assembly, but it is there. Like we don't have exactly everything on here. But so this top section, can anyone tell me what's going on here, what it does, why we have it? If not, I can explain it. Guys, please. Yes, that is correct. So we're initializing x to 5 and y to 8. And this DQ is basically just saying quad word. So then we have this text section, global start, which basically, remember from earlier, is like main. So we're going into our int main section. And over here, this is pretty self-explanatory. We move x into RAX, move y into RVX. I'm treating these as kind of arbitrary registers right now, but they'd probably be moved into different ones if this was actually done by a compiler, but it was written by me. So then we compare them, and then we have this JLE statement to L0. Can anyone tell me what JLE does? We just covered it.
If RAX is less than RVX, you jump down to the L0.
Yes. So that's basically what's going on here. So, and we can see 5 is indeed less than or equal to 8. So basically we skip this and we move all the way down to here, L0. So right here we've got this. Remember, this is an Intel syntax. So we move 5 into RDX. And then we run mul RDX, which after that, what would happen? Remember, with multiplication, it multiplies whatever we have here by whatever is in RAX. So after we run this multiplication, what would the value in RAX be? Okay, so from earlier, I put x into RAX and x was 5. So what? Okay, was that just me hoping that people would answer? Probably. So it would be 25. Good job, everyone. That was really collaborative. So after that, we run this move quad word x, RAX, which basically puts the value of RAX into x. So after this, x will be, we can do this, I just did it, 25. Yay, good job. And then we return. So that is just the entire code. So I will pull up the C code really quickly. Hello, are we? Oh, there we go. I clicked the button. So there is basically the equivalent C code. It looks quite similar, except in assembly, you can see in an if else statement, else code tends to actually be above the if code, just because that's how assembly works. A little bit cursed, but that's how it is. And note, there is no BSS section on this because everything was initialized at compile time. So I'll pass it off to Nick.
Cool. All right, one more demo. Yeah, question. Here, let me go back.
Yes.
So what is it that, why isn't that use RAX?
That's just how mul is. That's just how the people who wrote assembly, they just said it will.
Yes.
Yeah. That's just how it always is. That's why I put x into RAX. But normally if x was in an arbitrary register, you'd have to put it into RAX and then you would run your multiplication. But I just wanted to conserve register space.
All right, let me set up this demo real quick. Let's see. I'm going to mirror these screens. 1 second. Hopefully, Zoom did not break when I did that. That would be no fun. Is it still showing on the Zoom? Awesome. Okay, cool. So we've got one more demo for you, which is converting some C code to assembly code. I realized I'm not prepared for this, and I didn't get out my little cheat sheet paper for me. So excuse me 1 second. while I grab that. Not that I couldn't do without it. Okay. Oh, sorry about that. Okay. All right. So, yeah, this is better if you're all interactive. Maybe we'll do a line or two of code at a time by one person. Actually, okay, we'll start with the variables. How about these first 2 lines? If we want to write these two lines of C code and assembly code, anybody have a suggestion for what we do, where we put it in the assembly code?
People on Zoom too, you're not getting away.
Do you have any Zoom suggestions? We have one person on Zoom. What do we got? Any suggestions for just this first line?
I should have bought candy at Trader Joe's.
Candy would have been a move. Yeah, what's up, Benson?
Don't exactly remember the syntax.
No worries.
We had to set A, B, and oh, sorry. So since A and B are initialized at compile time,
Perfect.
in the data section, we have A, B, and rest the word, and then 46.
Awesome. Okay, so perfect. In the data section, we're going to want to declare A and B since they're the initialized variables, as Benson said. So we're going to write our A variable, and then we want, in this case, it's an int. So that's actually 32 bits of memory. So if we remember, a byte is 8-bit, or sorry, oh yeah, a byte is 8 bits, but a byte is 8 bits, a word is 2 bytes or 16 bits, and then a double word is 32 bits or what, 4 bytes. So this is a double word for an int. This is just a little fun fact. Ints are 32 bits. So we're doing a double word, and we're going to put 46 in it. And then B is also a double word. Oh, no, not BSS. B is also a double word with 3 in it. And then C, I'll just do that one real quick. C is also a double word. It's also an int. In this case, it's resd, and we're going to put 1 in there because that's, wait, yeah, we're going to put not 1 in C, but this is declaring 1 double word of memory for the variable C. All right, we're gonna move on to the code section. That's the actual code. Let's start with this statement right here. So in C, we can write all of this in one line, which is really cool. You may not think of C as like a very high level language, but in this case, it's very high level compared to assembly. This is actually gonna take a few lines. What do you suggest?
Quick question. In the slide, you did a demo where you assign x and y to 5 and 8 by using the term DQ. You're going to use DD to assign the variable?
Yeah, it should have been DD, my bad.
Well, yeah, and either way works. So DQ is a quad word, DD is a double word. A quad word is 64 bits, a double word is 32 bits. In that case, we were just using a quad word because, I don't know, it's easier sometimes. That was just doing 64-bit operations. You can use any size of data you want. In this case, just because I'm trying to like have it be exactly the same as the C code, I'm using the same variable sizes. Conventionally, an int is 32 bits, but it's fine that it was slightly different because you'll still get the same result. Yeah. So starting here, we're doing C equals A plus B. Any suggestions on how to start on this? Keelan knows what's up. Okay, so we start by putting them in registers. So let's put A into a register. So I'm going to put, and note, since we're using a double word, as you pointed out, we're going to use the EAX register, which is that lower 32 bits of the RAX register. And we're going to put a double word of A into that EAX register. And then what do we want to do to that A that we now have in the register? Okay, so we're gonna add, yes, indeed, we're gonna add to EAX that register. Oh no, EAX, we're gonna add B. Perfect. So now the result of that is in the A register, the RAX register or EAX, and then we're gonna put that value back into C, as we see right there. We're doing C equals A plus B. Here, let's zoom in a little bit. So we're gonna move that value back into C from EAX. Oh yeah, and I will note once more, this is all Intel syntax on the syntax that you'll do in CS33. If you're taking that right now, it's the order is flipped. So you'd actually do keyword A, move into EAX. Sorry for giving you the wrong ideas with this one, but it's not too hard to translate between the two. What's up, Roy?
Wait, that means that it's the very beginning of the block. the syntax the same in ACM for
I believe it's the same. We'll also send out like a link that has the comparisons. It's not too hard to translate between the two. It's the same, yeah. All right, next one. This one's easy. Bonus points for whoever gets this one. I mean, I don't know. B++, what do we got? How do we write that one?
There is an operation that lets you do it in one line.
It's a one-line operation, as Selma said. Not quite, good guess. Leah is load effective address. So you're doing, when you use Leah, you're dealing with memory addresses for the most part. In this case, we just want to increment a value of a variable. So how do we do that? Yes. So one thing you could do is add. I'm not entirely sure. I don't remember. It might not let you add like an immediate, so a number you put in the code directly to a variable. So it might let, I think it might allow you to do that. Yeah. And then the other way you can do it is just inc d word b. Those are both equivalent. One will increment it, one will do b++, the other one will add one. Same thing, whatever. You can use whichever one you want. Let's do b++. That's what that is. And then c minus minus, or sorry, not c minus minus. We have a minus minus. Similarly, you could do sub d word a1, or you could decrement d word a. All right. Next bit of code is a for loop. So this is kind of interesting. We remember how for loop works in C code. We can kind of break this down in assembly with a bunch of different steps and specifically jump statements, right? So anybody have a suggestion on how to start with that? What is the first thing that a for loop does, and how can we do that in assembly code? Yeah, Benson?
I think you may have to check a particular condition first. So you have to check I value is sort of down so you have to check if I is less than 0. Because if it's less than
Yes. Okay. So two correct things here. So yeah, Benson's talking about the second part of the loop, which is super helpful. James, yeah, first part, you want to initialize it, and then yeah, you want to compare it. So we'll initialize our variable I. As you saw earlier, I didn't actually put I at the top here. And the reason is, by convention in assembly, you use the C register for iterating through loops. So in this case, we'll do move, what am I doing? RCX, which is the C register. We'll put 0 into it. So we're starting our counter at 0. You can remember C is kind of the counter register. And then as Benson was saying, we want to compare it with really what's in the value of B, right? We want to compare our I value to what's in B. And so what we're doing is we're comparing our register, ECX. Oh, what am I doing? Okay, fun note here. I did move RCX 0, which means I'm putting 0 into the entire C register. But then because B is, as we saw earlier, a double word, we only want to compare the lower 32 bits of it. So that's why we're doing ECX. Those all are the same register though. So we're comparing that to. No, it just. No, it'll just give you an error.
Okay, so they have to be the same size.
They do have to be the same size. There's some cases where you can do that. We didn't cover it today, but if you want to say move a byte into a, I don't know, a whole register.
Okay.
So if you want to do like move, well, yeah, even if you wanted to move like C, for example, into the RAX register, the whole thing, there's the move ZX command, which allows you to do that. But there's so many instructions on assembly, I figured we wouldn't get into that today, but that is possible for some things, yeah. So we're going to compare ECX with B. And yeah, again, that's 32 bits. We're only comparing a double word worth of B, so we're accessing those 32 lower bits of the register. And what do we want to do with that comparison? Actually, I'm just going to write this out. So first off, we're going to have our kind of start loop code here. So what I'm going to do with this is well, it's the beginning of the loop. So our initial condition with for loops, like we have here, is only run once at the beginning of the program in C. So we're only doing that once. But then every time we loop, we kind of want to check our comparison again, right? So then what do we do if the comparison fails? And how do we check that? Yeah. Perfect. So if we have a label at the end called end, then we can jump and see if this comparison fails. So in this case, we're checking that I is less than B, so we want to jump when I is greater than or equal to B. So that would be J, G, E, jump greater than or equal to the end. Awesome. Okay, so that's our loop logic. Whenever we start the loop, we get our counter variable. Oh wait, actually one more part. Okay, yeah, that's our loop logic. We start by initializing I to 0, or in this case, our counter variable, or actually register RCX. And then we do our comparison. And if our comparison fails, we jump to the end. The last little bit of our for loop logic here is I++. So as we saw earlier, we can just do inc RCX at the end of our loop. And we want to do our comparison again once we get to the end of the loop. So we'll actually have a jump statement here to go to the start of the loop. And now we can actually get into the loop logic. That should be a little more straightforward. Let's do our C times equals 10 statement. Any suggestions on this? We can look back up at C equals A plus B. That'll give a good little hint. Pretty much, yeah. So let's see. I'll just copy that down, yeah. So we want to copy our value into the AX register, and then we're actually just going to mul by 10, and that'll put that back. So that'll, yeah, you're copying C into the AX register, and then you're multiplying what's in the A register by 10. And then, oh wait, is this going to work? Yeah. Oh, what am I doing? Oh, okay, okay. Sorry, one more little technicality here. We're specifically dealing with 32 bits, so we have to actually deal with those. We have to do 32-bit operations. So I'm using one other register, which is the EDX register. I'm going to put 10 into that. And then the compiler knows that we're doing a 32-bit operation when we multiply by EDX. Then we have our result in EAX, because that's where multiply just places the result by default. And we can just copy that back into C down here. For A divide equals 5, it's a similar process. We'll copy A into EAX, and then we will, okay, so as Selma was talking about earlier, divide actually goes across 2 registers. So you have a number that starts in the D register and then goes all the way into the A register. So we want to clear out that D register, EDX 0, so that it's just what's in the A register. The point of this is if you have a number that's, so these are 2 32-bit operations. If you have a number that's 64 bits, you want to divide it by only a 32-bit number. So it lets you do a whole 64-bit number by combining part of one register and part of another register, and then dividing by a 32-bit number. So in this case, we're just dealing with a much smaller number that's only fitting in the A register. What's up, Benson?
So the reason for that, EAX are both 32 bits. We have to wipe it completely for the entire 64-bit one because the upper 32 bits could possibly anything.
Yes, that's precisely it. Yes. So as Benson was saying, we have a value that's going to be in our, whatever the number that comes first in division is going to be in both the A register and the D register. And only the lower, we're only interested in the lower 32 bits, but we don't know what's in those upper 32 bits. So we want to clear that out to make sure that it's all zeros up there so that we have the number we're talking about. Then we can divide by 5 is what we want. Since I want to make sure that it's 32-bit division, I'm going to move this into another register. If you recall from earlier, we had registers at the end called R8, R9, etc. R8D will just give us the double word portion of the 8th register, well, the register labeled 8, the 9th register. We'll put 5 in that, and then we can divide by that. And yeah, like multiplication, division automatically puts the result in A, as we covered earlier. And it also puts the quotient in D, if I remember correctly. Yeah, cool. So depends on your sizes. Yeah. So then we will take that value of the result, which is in A now, and we'll put it back into our variable A. So it's in the A register, and we're putting it in the variable A. So move back into A, the value in EAX. And yeah, we're pretty much good here. At the end here, I further have some code that just ends the program normally. Assembly by default will just crash when it finishes. You have to add in a little more code that'll make it end with a 0 return code, make it end happily. Any questions about that demo? Yeah, what's up?
What word width does null default to if you use the literal downloading it into the
That is a good question. I'm not sure if you even can. Yeah, use a.
Multiply does not take immediates.
you can't multiply literals, period.
I think you just
You
can't
can
multiply intermediates.
if you
Yeah.
do source destination immediate. There's like a specific
Yeah.
format in IMO that will allow you to do that. And then that will, I believe, take on whatever the destination register is. But normally you cannot use immediates, multiplication, or in division. It will not like that.
Yeah, and that one version works because it gives one of the sizes in the actual operation. All right, any other questions? Cool, let's see, slideshow. Oh, that's not the slideshow we want. Where is the slideshow we want? I know, I am mirroring. Where's the original? That's so funny.
Right there.
Oh, you're so right, desktop 1. Let's go. Okay, we'll full screen this guy. Hey, go away, doc. Okay. Yeah, solutions on the slides too, which we'll have pretty soon. Oh, a couple other
Oh,
things
cool.
before we finish up.
PHLA actually made the buffer buffet simulator. So if you want some help on the like basic things like for loops, I think they do like while loops, addition, subtraction. You can look at the differences between the C code and the assembly. You can actually step through them and they show you what is stored in each register, what the flags are, stuff like that. I think it's helpful to visualize it. Buffer buffet, cool.
And yeah, that's all. That's all we got. Any further questions? Join our Discord. Oh, what's up?
This is like a general question, but like now, what professions or fields do people still like write assembly code?
It's really rare. It's not that common of a skill anymore. We learn it primarily so that we can just have an understanding of how computers work. I think there are a couple fields though, like maybe if you're working on writing drivers for a new device, like a graphics card, you're going to need to know assembly at least a little bit to work on something like that. There might be some other applications I can't recall off the top of my head, but it's not too many. Cybersecurity, exactly. If you're going to come to our CTF at PBR, Sci Row, then you might need it there to solve some challenges. But yeah, it's mostly just getting a better understanding of computers. And yeah.
Usually you're not going to be writing it, but you are going to be reading it. Like say if you're doing, I believe next week we have our reverse engineering workshop. So you're going to be looking at assembly code there and trying to figure out what it does. A couple of our challenges have you reading assembly. So writing assembly basically helps you get a better understanding of how it actually works so that you can read it better, pretty much.
Did you have a question as well?
I was just going to chime in and say that any kind of reverse engineering or decompilation requires some kind of assembly knowledge. Especially because we don't have these compilers that are perfect. Compilation is always going to be lossy. So you might have to sift through assembly and find a translation back to a higher level.
Yeah. Awesome. Anything else? Sweet. Yeah, thanks for coming.
Oh, where's the button?
We have some challenges on the website if you want to try those out. Also, the data lab tutorial has started, so if you want to join that too, either's cool.
Yes. Okay, I'll have this back up in a second.